Good morning, everyone. Today I will present our paper titled NICScatter, Backscatter as a Cover Channel in Mobile Devices. Nowadays, our mobile devices collect a lot of our sensitive information, such as our fingerprint, credit card information, and the various online accounts and passwords. We want to know that whether our information is safe with our device. In order to achieve this purpose, we may use firewalls and network monitor to guarantee that this information does not go out of our device. For the extreme case, we may keep this device disconnected from the internet. We may keep this device in a safe region without public internet connection. This is the common practice in military and the banking system. So, we want to know, given these protection methods, are our data secure enough? Unfortunately, the answer is no. Our data is still under risk given these protection methods. In our attack scenario, the victim could be a smartphone or a laptop. We assume that a malware has been installed in the victim. An attacker nearby can receive the information transmitted by the malware, just like what we show on this slide. We show that the attacker can receive the data sequence transmitted by the malware, which is the 0101 sequence on this slide. So how are these bits transmitted? The fact is simply that the malware in the victim forces the victim to reflect instant RF signals, just like a passive backscatter tag. In this talk, I will talk about this cover channel. I will first introduce how we enable backscatter communication using commercial mobile device. We enable backscatter communication using commercial Wi-Fi NICs, so we call it Wi-Fi NICScatter. Then we will discuss the system vulnerabilities in current Linux and Android systems, which enable us to stealthily enable NICScatter as a cover channel. Before going to the details, let's review how backscatter tags work. On a backscatter tag, there's a dedicated circuit. On the circuit, there will be two load impedance. The tag will switch its antenna load impedance between these two states. In one state, due to the mismatch between the antenna impedance and the load impedance, the antenna will be refracting signals. When it switches to another state, the antenna will be absorbing signals. So, by switching between these two states, the tag is able to transmit 0101 data sequence. This is the working principle of backscatter tags. However, on a commercial device, we do not have this dedicated circuit. How could a commercial device emulate the behavior of a backscatter tag? We observe that when the Wi-Fi NIC is in different working states, it has different load impedance. To do the measurement, we connect a Broadcom Wi-Fi NIC to a vector network analyzer. We found that when we turn the NIC from off to on, its impedance will jump from one region on the Smith chart to another region. This indicates that the impedance when the Wi-Fi NIC is in off and on states are different. So we can use these two states to emulate the two states on a backscatter tag. This is the working principle of NICScatter. Now let's look at the reflection properties of Wi-Fi NICs. On this slide, we show their impedance when in different states. The first example is the Broadcom model. When we turn the NIC from off state to the on state, the real part of the impedance value will jump from about 12 to about 100, while there's no significant change in the virtual part. By calculation, we can get that it will cause about 6 dB loss during refraction. This number is comparable to some dedicated backscatter tag. The second example is the Intel model. Similarly, by calculation, we can get it will be about 18 dB loss during refraction. This number is larger than the previous one because it has a smaller impedance change when we're switching states. This number is also the refraction loss is also the largest among all the models we have tested. In evaluation, we show that with this Wi-Fi NIC, the effective communication distance is up to 2 meters. On this slide, we show the detailed waveforms when we're switching the Wi-Fi NIC's working states. For the Intel model, when we switch it from on to off states, it will jump from one value to another value. For the Ethos model, when we switch it on, there will be a rapid change on the intensity, but there will be no significant change when we turn it off. Given this characteristic, we use on-off position modulation to encode data. We divide the time into equal time slots. In each time slot, we will first issue an off-to-on command and then an on-to-off command to generate an on-off pulse. We use the precision of this pulse to encode the data. If the pulse happened as the second half of the time duration, we encode it as bit 0, and when it happens at the first half of the time duration, we encode it as bit 1. This is how we encode data in NICScatter. Another diversity in Wi-Fi NICs is their execution latency. On this slide, we compare four Wi-Fi NIC models. The normal execution latency is about 0.02 seconds. One exception is the Intel 5300 model. Its execution latency from off-state to on-state is about 0.17 seconds. In order to incorporate the Intel model in NICScatter, we set the time duration of the OPM modulation to be 0.5 seconds, which means that the maximum throughput we can achieve is 2 bps. If we exclude the Intel model, we can significantly boost the throughput. So for a quick summary, we found that the refraction property for the same Wi-Fi NIC is consistent. However, for different Wi-Fi NICs, their refraction properties are different, even though they may come from the same manufacturer. So far, I have introduced how we enable backscatter communication using commercial Wi-Fi NICs. Now let's look at the system vulnerabilities, which can stealthily enable backscatter communication in both Linux and Android systems. First, let's take a look at the Linux system. In Linux system, the vulnerabilities comes from the RFKILL Subsystem. The RFKILL Subsystem is originally designed to manage all the RF/IO devices. The airplane model, which we are very familiar with, is implemented using the RFKILL Subsystem. The interface to the RFKILL Subsystem is a device file, also called RFKILL. When we write command to this file, we can change the working state of RF devices. So if we write RF block Wi-Fi, it will turn off the Wi-Fi NIC. Similarly, if we write RF unblock Wi-Fi, it will bring up the Wi-Fi NIC. The problem here is that the writing permission of this file is open to all users, which means that the operations of NICScatter does not require any special privileges. It's kind of weird that we have this kind of loophole in Linux system. We read the related documents and found that this permission is granted in order to incorporate a special Bluetooth manager. I will not go into details here, and if you are interested, you may read the paper. We report this because we think this should be known to the public. Then let's look at the Android system. In Android systems, operation permissions are classified into two categories. The first category is the dangerous permissions. It requires users explicit grant during installation. For example, if an application wants to access the user's calendar or camera, there will be a pop-up information to inform the users about the potential risk during installation. Another category is called normal permissions. It will not notify the users when during application installation. To operate NICScatter, we need a system service called Wi-Fi Manager. To operate Wi-Fi Manager, the operation permission is called Change Wi-Fi State, which is classified into the normal permissions. This means that users are totally blind on whether an application could possibly establish a covert channel using NICScatter. So far, I have introduced how we enable backscatter communication using Wi-Fi NICs and the system vulnerabilities in current operating systems. Now let's look at how we do the evaluation. We put the victim and the receiver on a desk, and the helper is placed above the desk. The helper could be any dedicated signal generator, or it could be a commercial Wi-Fi AP. In our evaluation, we will change the distance between the victim and the receiver, which is the D2 on this figure. In our first attack scenario, we use a USRP as the signal helper and another USRP as the attacker to decode the refracted signal. We use a laptop as the victim. The laptop has the Intel 5300 model. Here we show the relationship between SNR and the distance. We can see that with the increasing distance, the SNR is generally decreasing. However, there's some small fluctuations. We can see that the effective communication distance is about 2 meters. As I mentioned before, the Intel 5300 model has the smallest impedance change, so we believe that if the victim is using other Wi-Fi NICs, the communication distance can be larger than this value. In our second attack scenario, we replace the victim with a smartphone. Here we also show the relationship between SNR and the distance. In this case, the effective communication distance is about 20 centimeters. This number is smaller than the previous case. One possible reason for this is that due to the compact antenna design in the smartphone, thus it has a smaller antenna gain. Although this number may sound very limited, we believe that there are still scenarios where NICScatter can do bad things. For example, when we are making mobile payments, we may put our phone really close to a reader, which may be malicious. In this case, the NICScatter can establish a covert channel and link the user's sensitive information. In the last attack scenario, we use a commercial AP as the signal helper and use another laptop as the attacker. Here we decode the signal using RSSI and CSI. The RSSI and CSI is obtained from the CSI tool. Under this scenario, the effective communication distance is about 33 to 40 centimeters. This number is also smaller than the case when we use dedicated device because CSI and RSSI has lower resolution and a small dynamic range. Finally, I will discuss some limitations and discuss potential applications of NICScatter. One obvious limitation of NICScatter is its communication distance. There are many factors that will limit its communication distance, such as its impedance change during NIC switching and the antenna gain. However, the most significant one should be the interference from the signal helper. We can leverage some interference cancellation technique to boost the communication distance. The second limitation is about the data rate. The data rate we can achieve with the NICScatter is limited by how fast we can switch the working impedance of Wi-Fi NIC. It is not hard to imagine that given the complex processing techniques when we turn on and turn off Wi-Fi NIC, it will be a large latency. So we are looking for more faster operations, such as channel switching, which could also bring impedance change, but it operates much faster. Finally, as a general backscatter technique, we believe that NICScatter can achieve more than a cover channel. For example, we may use Wi-Fi NIC to backscatter Bluetooth signals to enable cross-protocol communication. And given the mobile device has the capability of NICScatter, we may enable interesting applications in wireless sensing. That's all for my presentations. Thank you for listening, and I will take your questions.